Hello and good afternoon. I want to start by thanking the conference organizers for giving me the honor and pleasure to speak today, as well as the audience for spending your time to learn about my work. What I'm going to show you today is an approach that we developed that improves upon current methods for predicting protein-protein interactions, which we then leverage to assess whether and to what degree cell specificity impacts protein assembly. Starting from the well-characterized complexes in the public repository, Quorum, we generated a list of pairs from every protein across all complexes. Then we assign labels, interacting or non-interacting, based on whether they were co-occurring in any complex. Our goal was to predict whether a pair interacted using a combination of heterogeneous complementary features. Our prior work and others have shown that incorporating diverse yet complementary data, like the ones we used, shown here, enhances predictive performance, and we're leveraging the collective strength of various modalities, that is affinity purification, mass spectrometry, co-expression of RNA or proteins, to compensate for each one's methodological biases, their susceptibility to variability, and in general shortcomings. However, we also demonstrated that rather than relying on direct measurements alone, well established among classical studies, combining them with indirect measurements improves accuracy and expands the coverage of possible interactions. However, for each pair of proteins, some features will probably be unavailable and is missing for training, let alone testing. A typical approach to addressing missing features is imputation, in which estimates or constants are used and to serve as substitutes. We propose an alternative framework. We rely entirely on available data and seek to extract as much mutual information from joint data sets as possible by training a random forest for every subset of pairs and features such that there are no missing features for any pair. Afterward, we calculate a score for every pair from the weighted collection of its applicable predictors. Finally, by ranking pairs based on the model's confidence in their interaction, we use the labels from Quorum to generate precision recall curves over a range of thresholds. And now I'm going to show you how our performance changes as we incorporate progressively more diverse sets of features. This graph shows two of the preceding motivating studies results, Drew et al. From 2017 and Lugo Martinez et al. In 2019, our group. For comparison, along with the performance of our new method for model interactions as we iteratively introduce progressively more diverse features. The first set of features originated with the Drew study in 2017, and I'm characterizing those features as KD. The second set of features corresponds to Lugo Martinez 2019, and I'm characterizing those sets of features as LM. And then as we move down the legend, we then start seeing the features new, which are features that which is a group of features that we added for this study, as well as a set of features from subcellular barcode. Now, as we compare our results to the first preceding studies, we find that with just the Drew set of features, we're already comparable. We're already achieving comparable performance to those studies. Next, when we add features that were introduced by Lugo Martinez, our model immediately begins to outperform the others. Finally, as we add the new combination features and subsequently the set of features from subcellular barcode, we see that it's clear, it's evident that we're making a dramatic improvement. So now, having shown that we developed a technique which is producing interactions with high quality predictions for interactions with evidence in Quorum, we're now prepared to make predictions for novel interactions. I'll note here that our method combined with indirect measurements allows us to make predictions for interactions that would not be possible in a direct protein-protein interaction study. It's at this point that we decided we were able to substitute cell line specific data for features in which it was available. And so we moved on to predicting what pairs would interact in a particular cell. We had available data for the cell lines shown here. H322 corresponds to lung tissue, MCF7 corresponds to breast tissue, and U251 corresponds to neural tissue. Our model produced interactions across all three cell lines that were shared broadly, that were shared in common. Nonetheless, when we took the symmetric difference of interactions, and that is the sum of interactions between two cell lines that are exclusive to each of them, we found that approximately 10% of each cell line's specific predictions were exclusive to each cell line. Moving forward, we decided to find what protein complexes we could generate from cell line specific interaction predictions. But first, let's discuss how we generated complexes and how we evaluated them. Using graph-based methods, we clustered the pairs based on whether their scores meet some threshold. We determine that empirically. As a reminder, a score is the model's confidence that a pair of proteins will interact. Now, before we could investigate what impact the differences cell line specific predicted interactions could have, we needed to assess the accuracy of our predictions just to the interactions. The measure we used is called the K-clique weighted F1 score, and this came from the Drew 2017 study. Its purpose was to allow us to compare predicted complexes to benchmark or reference complexes. The problem that's presented with this task is that we have two collections that we want to compare, and each collection is comprised of differently sized objects, complexes in our case, of different lengths. They solved this problem by refocusing on evaluating the interaction proteins instead of on the proteins themselves as distinct elements. This measure is made possible by calculating precision and recall iteratively for the range of predicted complex lengths over the complete collection, all possible combinations of complexes of length k, K-clique, of length k between the predictions and the references. We then calculate a global F1 score from weighing the precision and recall for each length for each k between 2 and n being the highest or greatest length for prediction. We then weigh the precision and recall for each length by the number of clusters predicted at each length. And this weighting is important because it counters the bias that's introduced by increasingly larger and larger sets. We compared the K-clique weighted F1 scores for our predicted complexes to our prior work as well as to the Drew 2017 study. Using their reference complexes for both 2017 and 2021, the more recent study. We were curious as how the complexes predictions would perform against their more recent 2021 study. So considering that they updated and added new features themselves, so we found our results using the 2017-2021 references were exhibiting a range for which there were superior performances by some of the assemblies, and in particular, a major increase in performance for cell lines MCF7 U251. Furthermore, the protein complexes generated from taking the mean of the model's prediction strengths matched that for the three cell lines, matched that of the most recent study by Drew. At this point, we were ready to investigate how cell line specificity-driven differences could impact protein assembly. As before, with cell line specific interaction predictions, we observed that most predicted complexes were shared in common, and a similar fraction of each assembly's complexes were exclusive to one cell line. So in conclusion, we were able to come up with an improved model. We found that we could indeed learn cell line specific models. that could have comparable performance. And we also were able to find, most importantly, that using our modeling, that cell line specific features taken into account for interactions do impact subsequent protein assembly. Again, thank you, and I look forward to meeting and collaborating with many of you as the conference proceeds.